Welcome, everyone. Welcome to lecture 8 of the elements of machine learning, or perhaps it's lecture 1 because, hey, this is the first lecture that you're not being taught by Dr. Kligerman, but by myself, Gilles Vreken. I'm looking forward to taking over EML from this moment onward, even though it is a pity that this lecture I can only pre-record, because at the moment where you should be in the lecture hall, and I would normally be on stage to explain all the things I'm going to explain, I'll be roaming around in New Orleans to attend NeurIPS. NeurIPS is one of the most important conferences in the wonderful world of machine learning. It's the conference for neural information processing systems. That is a bit of a stupid name because it's more like everything that has to do with machine learning, but they probably couldn't find a good acronym for that. Anyway, lecture 8. It is Thursday, both for you as well as for me. And well, let's get started. What is the topic for today? Well, we plan to go boldly beyond linearity. That is the goal, or the official title of the lecture will be Beyond Linearity, or Beyond Linear. Because so far, we've been primarily focusing on some very basic techniques, really truly the elements of machine learning. Linear regression, logistic regression, which is just linear regression with a logistic function. And well, we did a few things that seem to push us beyond linear, but right now we're really going to go much, much further. So how can we extend linear models? You've seen one general approach, namely basis functions. You've seen polynomial regression, where we use polynomial basis functions. So rather than just the pure input features, we also use x squared or x1 squared, x3 squared, x4 cubed, and so on and so forth. And that allows us to use the same machinery from linear regression. And all of a sudden, we actually get functions that are nonlinear in the original input space. That is pretty amazing. So, okay, cool. Are these truly nonlinear? We will get to that in a second. We're going to be discussing in today's lecture a few other techniques. One is step functions. Step functions are, well, a super simple way to make a function nonlinear, namely up till from here to here we use one function, and from there to there we use another function. That's that. I mean, step functions. We split our input domain in k distinct regions, and for each region we have a different function, and that's that. For example, k nearest neighbor is one way to do this, but we'll see a few others in the course of the lecture. Now, in a step function, you have a constant value for a region. That is, of course, a bit limiting, right? And so why don't we take this idea of splitting the input domain into regions and fitting a function per region a little bit further? That is actually the key idea behind regression splines. We divide the input into k regions, we fit some function, typically a polynomial, but hey, whatever you want will work in the end, I mean, if you do the math. So let's stick with polynomials for now. We fit a polynomial, and then, well, in order to make the entire thing look a bit more like one single function, we apply some magic to tie these functions together at these split points. Then, fourth, we push this to the extreme, and those are smoothing splines, where we don't say that we have k distinct regions. No, every point gets its own region. And then this tying together starts to become really important. But effectively, smoothing splines are just regression splines with many knots. Regression splines are just simply step functions. And yeah, okay, essentially we'll be talking about step functions all lecture long, except for local regression. Near the end, right before I start to talk about generalized additive models, we'll be discussing local regression. Local regression is simply the idea that, hey, well, for a point of interest where we want to predict, we simply gather from the data the k nearest neighbors, so those points that are closest to what we want to query, and now over these k nearest neighbors, we fit again a function. So now, depending on where in the data we query, we get a different function, and hey, we really are moving beyond linearity. Now, generalized additive models, they combine all this goodness into one. That I'll discuss hence at the end. Let's start with the basics. You already know polynomial regression. It's just linear regression where basically the standard model looks like this. And in polynomial regression, we add some basis functions. So rather than just having one coefficient for xi, we now exactly have, well, beta 1 for xi, but we also consider xi squared. We have another coefficient for that, all the way up till whatever the degree of polynomial we choose. So if we choose 3, then well, we have plane xi, we'll have squared, and we'll have cubed, and so on and so forth. Now, on the one hand, the function we get is nonlinear. Obviously, it can be way more wiggly than just a straight line. However, the model, if you look at it, it is still linear in the coefficients beta. So beta I, beta, or beta 1, beta 2, beta 3, it's still linear. We just have some coefficient time a basis function over an input. And we all add them together. So it is still linear in the coefficients beta. Just to give an example, here we have a sample regression where we have, I think, degree 4. These degree 4 polynomials, you can see it fits the data quite well. I mean, the really high earners, I mean, they don't fit so well, but okay, that's all fine. One thing to note, and we will get to that again and again, is that here at the ends, our predictions are, well, way less reliable. Obviously, here in the middle, we have way more data to fit the model, and that results into much tighter confidence intervals. These are the 95% confidence intervals, or the confidence band, as you can also call it. And as you can see around here, it's very tight, but here at the ends, where we have much less data, they start to widen quite dramatically. This means that any prediction of this function we're going to get, you get a value, but it starts to get more or less random. You need to be careful there. This is going to be worse and worse and worse the higher you crank d, the dimensionality or the degree of your polynomial. Because the higher d, the more wiggly polynomial you will get. And if you fit a super wiggly polynomial on very little data, you're not going to have a good time. How do we compute these confidence bounds? Well, the nice thing about polynomial regression still being linear in the coefficients is that we can use all the machinery that you've learned in the previous lectures. I'm not going to repeat those. You can just use exactly the same. I already mentioned something about the high earners. I mean, that's let's move on. We also discussed classification in the previous lectures, and exactly the same thing holds right now. If we use basis functions and we just plug them into logistic regression, well, we do have, on the one hand, a model that can be wiggly. It's not just a straight line, but at the same time, it is still linear in the coefficients beta. So what you see there is, again, if we now have a logistic regression, we want to predict if somebody makes a lot of money, so there's the group at the very top, which, as we already saw, the model doesn't fit that well, right? I mean, the line did not really go quite well through it. You see that, well, you have quite high, and especially at the very high-aged population, very wide confidence intervals. Basically, the model has no idea what it's doing. It's trying its best. That's all we can say. So, why doesn't it know anything? Because we have very few people of that age that make that much money. Or we basically actually have very few people at that age to begin with, and hence it's very difficult to train a model. So, good. So that was polynomial regression in action. How do we now choose the degree? In practice, for polynomial regression, I would recommend to use a degree of up to 3, perhaps 4, if you feel lucky. So the key problem is that the moment you start to choose your degree too high, then, well, the polynomial becomes too wiggly and you can fit essentially any function. And that includes the noise in your data. You will very quickly overfit. I mean, if you have a polynomial of degree n, you can fit n observations essentially no problem, right? I mean, you can have a unique fitting of the noise. That is not going to lead to a good time. Now, in practice, how do you choose, right? If you don't want to just choose 3 or 4, just put it out of thin air, you can use cross-validation. You can choose, well, for different values of d, I mean, to do cross-validation and choose the one that predicts best. That's your to get best score. That works in practice. But in practice, you will often just resort to a polynomial of degree 3 or 4. That's what my experience is. One side note, where I say that, hey, there's a risk of overfitting, this is absolutely true. Absolutely true. And that's everything we've been telling you in this course is true. However, more modern insights, when you have models with extremely many degrees and you train them the right way, then actually, even with much higher degrees of freedom, not necessarily for polynomials, but models that are like super wiggly, deep neural networks, then actually it is absolutely fine, again, to have a degree of freedom that is much higher than the number of observations. You still get good models that can generalize well. Note that I say can, because you need to get many things right. In this course, we ignore this for now. Maybe at the very end, get back to this again. At the very end, I mean, end of the course. Good. I already pointed out that with a high degree of your polynomial, with a very flexible model, at the tails of your data, basically where you have no evidence beyond, for the very old people, the people that earn really a lot of money, where you have little data, you get very bad behavior, you get very wide confidence bands, and you basically should not trust your model. So always determine confidence bands if you want to apply a model. And in the extreme cases, just don't trust your model. But, you have to resort to voodoo or to a crystal ball, but don't use high degree polynomials. Okay, let's move on. Step functions. I already quickly introduced them in the very beginning. What we do, well, effectively, we take a continuous variable, let's say age, and we turn it into an ordinal variable. So it's categorical, but it has an order. For example, age group 0 till 10, 10 till 20, 20 to 30, 30 to 40, and so on and so forth. Each of these groups, or actually particularly these split points, we call them cut points, C1, 2, 3, and so on and so forth. They define together these bins, right? So effectively what we're doing with a cut point, we're creating a new variable. Namely, is the value, and this is an indicator variable, is the value of x lower than cut point C1? If so, well, then newly constructed random variable C0 of x will be 1. Same thing for if the value of x is between C1 and C2, an indicator variable, so this thing will be 1 if this is the case, and then C1, our newly constructed dummy variable, will take the value of 1, otherwise we'll take a value of 0. If you choose your cut points well, and basically if you don't make a stupid mistake when implementing this, then obviously the sum of all these variables is going to be 1, because x can only take a value in one of those, right? And this is also why this is less than, and this is then less than and equals. Okay, good. Effectively, what we now have is we have now a problem where we can do regression, not over the original xi's, but over, well, does xi fall in C1, does xi fall in C2, and so on and so forth. We can simply apply all the machinery you've already know, love, maybe hate, but we don't have to do anything special. Is this model linear in the coefficients? Yes, it's still linear in the coefficients. Thank you for asking, but yes. What do we have? B0 or beta 0, beta naught is still the average of y, I mean, for all x smaller than C1. That's basically really the baseline. And the other betas, they're essentially the increases over that. Good. There's not so much to be said about step functions. I mean, they work. They're not miraculous because, yeah, the problem is, of course, that we just have these flat regions, right? There's not so much action within it. But, as you can see that, hey, here in the middle, we again have a very small confidence band. That is good, right? Lots of trust. Here at the end, less data. The confidence band is wider, but it's not absurdly wide. So if we do go to the classification case, which we can just do, because again, we have basis functions. We just constructed them slightly differently. We plug them into logistic regression, and there we are. Now, here we have, for different age groups, we have these cut points. Logistic regression determines what is now the probability of a certain of a person having a wage higher than. You can again see that for the very old people, for the elderly, right? I mean, the retired people, that the confidence band is again much wider because we again have much less data. This is something that's just inescapable. The width of these confidence bands, I'm not going to page back to the other slide, but it is much tighter than it was with the polynomial regression. Because effectively, the degree of freedom within this bin is 1. just what is the average? That's it, right? I mean, that's and because we only have to estimate this one parameter within this bin, yeah, well, even though we have little data, we actually do a pretty decent job. Okay, good. Now, the real magic, if you want to apply step functions, is of course where to place the cut points. And with that, how many? You need to, of course, put them in the right spots. That's it. So if you put them basically you need to put them where the action is. So if you have a blob of data, and these people all behave the same, and on the side you have blobs of data that behave differently, then you need to place the cut points really between these blobs. Otherwise, if you place them halfway these blobs, then you get weird averaging effect. You don't want that. So, how can you do this? Cross-validation. Cross-validation is like the magic wand that we can apply anywhere. So choose your favorite series of values for k, evaluate them, there you go. Now, where to place these k cut points? For that, I'm going to swipe this under the carpet for now. So just choose them wisely, and that's that. Because I'd actually much rather start to talk about regression splines. Regression splines, we're going to level up from having just a single value predicted within a bin to actually having a small function there, to a small polynomial function. So instead of having step functions with a fixed value, or what we did previously, having one polynomial to fit all of the data, and therewith, like, okay, well, perhaps in the middle you need a higher degree, but at the ends it's more flat. And it's like, okay, it's stupid to have a higher degree. Why don't we just fit a polynomial per bin? Well, simple idea, makes a lot of sense. For example, in the data we have here on the right, age versus wage. On the left-hand side, if we put a cut point at age of 50, here we have a parabolic function being fitted. And you see it fits the data quite well. On the right-hand side, for the elderly people, okay, well, this function also makes quite a bit of sense, right? I mean, confidence bands will again be quite large, but it makes sense to treat these two parts of the data differently. Now, here, what we're applying is quite simply a cubic function in each of these bins. That creates a weird discontinuity over here, right? And so if somebody is one day before their 50th birthday, we would predict that they have a wage of, what is it, 110,000 monies. But if they're one day after their 50th birthday, they all of a sudden predicted to make 150, that's a little bit odd, right? That is behavior that you do not want in your machine learning model. So what can we do? We can simply require these functions, so this is one polynomial function, this is another one, to spit out the same value at the cut points, right? I mean, we're the boss, we can decide this. So what we're going to say, we're going to smoothen the splines in such a way that at the cut points, they spit out the same value. The first approach that we do is that we just knot them together, really, and they have to give the same value. But note that this is still not smooth, right? It's not continuous. I mean, it spits out the same value, but I mean, it's not differentiable. So the next thing we can do is, we don't just require that they spit out the same value at the cut point, but they should have the same slope. In practice, what we say that we require this function to be continuous and d minus 1 times continuously differentiable. That is just a fancy way of saying that, okay, they need to have the same slope, right? But, where d is obviously the degree of the polynomial. Otherwise, you would still have some weird discontinuities in the way. Now, for a number of reasons, not in the least because it just works very well in practice, a degree of 3, so cubic splines, is a very popular choice. Essentially, in practice, you don't really need more. Why not? Well, if you really need more action to be modeled, then just choose more bins, a higher number for k, and just tie them together again. Because if you instead use a higher degree, then you get weird wiggliness. And are you really certain that you're estimating all your parameters right? No, let's just focus. Let's keep things simple. Works very well in practice. So cubic splines is a good compromise between nonlinearity on the one hand and smoothness on the other. Now, making the model more flexible by adding degree increasing the degree, might lead you to ask the question, what is the degree actually of a spline then, right? I mean, that's, if we have k cut points, we could also call these knots because we're not the functions together, right? So obviously what we're doing here, we're knotting them together. We have to fit k plus 1 polynomials. Now, if we choose a polynomial of degree d within such a bin, then the regression spline of degree d with k, this is quite simply degree of freedom of d plus k plus 1. So effectively, for a cubic spline with k knots, we have a degree of freedom, or dimensionality, you can also call this, of k plus d plus 1 is k plus 4. That's in this particular case. Okay, this is, you basically see immediately that actually even though we fit very simple functions and relatively many of them, the effective degree of freedom is much lower than you might expect, because you might have expected, hey, we fit a degree of d in this bin, so this is d, and here as well, that is twice d, and here as well, so basically k times d, or k plus 1 times d. Why is this not the case? Because we knot these things together. We require them to have the same value, the same slope. So the effective degree of freedom within a bin of the spline is much reduced. If I really need a function on the right-hand side bin that gives a very high value, otherwise, I mean, the fit is really bad, that allows or disallows the function to the left of it to give a really low value that really needs to be cranked up, and maybe the other one goes a little bit down, and then we need to make sure that so we lose degrees of freedom. Hence, the degrees of freedom, the effective degrees of freedom of a cubic spline is only k plus 4. And this is good, because a low degree of freedom allows us to estimate the parameters with much more certainty. So effectively, what we have is that I need a quick sip. I'm thirsty. Lecturing is thirsty business. Yeah, effectively, what we have for a cubic spline, what are now the basis functions? Well, we have just the intercept, of course. We have x squared, we have x to the power 3, because it's a cubic spline. But because we tie these things together, effectively, it is a truncated cubic function. So it doesn't have the entire degrees of freedom that you would expect it to have. Good. Now, if we want to fit a particularly wiggly function, then you might be tempted to crank k or d up. Let's see what happens. Because, so here we have on the right-hand side, let's look at the figure first. We have a cubic spline, right? I mean, the blue line, this is what we're interested in. And as you can see, we have a cut point around 25, one at 40, one at 60. And we fit this function, and this is the blue line, right? So ignore the red line, please. I sadly don't have a figure without the red line. Otherwise, I would have shown it to you. And this function fits the data quite well. But if we now look again at the confidence intervals, confidence bands, this looks actually pretty nasty. In the middle bins, quite good, right? I mean, it could be a bit tighter, but this is fine. So now, at the right-hand side, you can see this weird widening. It's weird. It's just, and here it's wide, and then becomes a little bit less wide, and then it starts to shoot off. Same type of behavior here on the left-hand side. Why is that? This is because we're fitting a cubic function, polynomial of degree 3, essentially on very little data. That's the natural effect on the bins on the end. And whereas in this middle bin, the effective degree of freedom of the polynomial is curbed because it needs to knot with both here and here, right, at both cut points, so that limits the degree of freedom within this bin, and that also reduces effectively the confidence intervals. And here on the right-hand side, yes, it is cut here. As you can see, this is also where the confidence intervals are not that broad, but at the right-hand side, it can do whatever the hell it pleases, and it damn well does. And this is where this degree of 3 is actually biting us a little bit in the back. The wiggliness, so the small bump that you see here, there's essentially no real evidence for this. Similarly, that the fact that this sort of takes a parabolic leap into the depths, there is no evidence for that. And that leads to this weird confidence interval behavior. So at the edges, we right now have wider confidence intervals than we want to. And this is because these functions essentially have, well, too much freedom at the tails. So, natural idea, let's curb their enthusiasm. Let's limit the degrees of freedom of the splines at the edges. So here at the ends, why don't we, well, we go now for a degree of 3. We could go for squared, but hey, if we have squared, why don't we just make it linear? Because effectively, the only thing we can sort of fit here is the general trend. And if there really is a more interesting phenomena to be modeled, then let's add another cut point. So the idea is, let's, for a natural spline, a natural cubic spline, is use cubic splines within any bin, except for at the edges. There we just use a linear function. And then we will have what we call a natural cubic spline. Now, these have naturally, slightly different basis functions, which I show here. I'm not going to go into detail because that is not so important right now for the story. We can think about what is now the dimensionality of the thing. Well, natural cubic splines have less dimensionality at the end, so k0 has the dimension of k. We lost something. We lost 2 degrees of freedom at each boundary region, and that trickles further into the degrees of freedom within the entire cubic spline. So rather than having influence of d, we're now really strictly at k. That is pretty neat, right? Because we still have quite flexible in practice functions, right? They can fit the data quite well, but we don't have to estimate that many parameters. They're really more curved. So effectively with natural splines, by fitting a linear function at this edge, we reduce the wiggliness at this point, and that permeates throughout the entire spline. So by fixing the problem at the ends, we also, in a way, well, fix problems in the middle, problem that we didn't really even have. Now, how is this fixed? Just look at the confidence intervals of the red dotted lines, right? So for the red function, as you can see, the red function is practically the same as the blue one, except it doesn't have this weird behavior of these bumps, which we want to get rid of. If you look at the confidence intervals, they are much tighter. Sure, they shoot off here, but yeah, that is natural because we simply don't have any data of anybody above, is it 80 years old? So that makes sense. So this is natural splines are a very good idea. Cubic splines are a really good idea. Natural splines are an even better idea. Now, let's go back to where to place the knots. How many and where do we place them? One approach that you can choose is you just think hard, you choose a value of k, or cross-validation guide you in which value of k to choose. You take your input domain, for example, age, and then you just split it into equi-width bins. So basically, you have your input domain, you divide it by k, and that is basically the bins that you have. You can also do it the other way around. You say, okay, well, actually, I want to make sure that in every bin, I have at least so many data points. So then we take n, we divide it by k, and then we just assign points. We fill the bin. We take the first n over k points and put it in bin 1. Then we take the second n over k points, put it in bin 2, and so on and so forth. This creates bins that are, well, not equi-width, but they are equi-height. If you were to draw a histogram, they have the same number of points. These are 2 very common approaches. The generalization, the second approach, is to distribute the data according to the quantiles data set. That allows you to have bins over the more dense regions of your data and then bins over the more sparse regions of your data. And that's a particularly good idea for natural splines, because there where the data is dense, we have then a cubic function of which we curb its enthusiasm. And at the tails where the data is sparse, we just fit a linear function, and that is going to be fine. That's going to be good enough. So this way, you can, in a very data-driven manner, put the cut points and hence the knots at where the action is without having to break your pretty little head over it. Now, the number of knots we still have to choose. And like I said, cross-validation is going to be your friend, as it's your friend for basically choosing any parameter in the entirety of this course, and perhaps even ML at large. the number of knots directly relates to the degrees of freedom of the model. Remember, for cubic splines, plain cubic splines, it was k plus d plus 1. So for cubic, k plus 4. And for natural cubic splines, it's just k. Right? So the higher we choose k, the more flexibility we can fit. What is nice is that, and we will see this in a minute again, we'll see this in a minute. We can compute either analytically, what is the degree of freedom of a model, and we can also determine it by its wiggliness. We'll see that in a few slides. And that allows you, as the user, to choose the degree of freedom. So basically say, okay, well, for this data, a higher degree of freedom is better, or I need a lower degree of freedom. And you can tune your confidence bands accordingly. Again, cross-validation is your friend. You just choose a number of k or different degrees of freedom. You see which one perform best, and there you are. Bob's your uncle, as they say in the UK. Good. So, effectively, we're then doing model selection, but for splines. So we're just taking things from the previous lecture, moving it into this one. So as you can see, the mean squared error for a natural spline, the number of knots. If you have one knot, well, you're just fitting a linear function. That is a stupid idea, right? Actually, yeah, that is a linear function because we have two linear parts. Then from a degree of 2, then it starts to become a little bit more interesting because we have two linear parts, and then, well, we have something cubic-ish in the middle, right? And so on and so forth. And as you can see that, well, just by the elbow rule, I think 3 would be the right choice here. Haven't determined it exactly. So maybe it's 2, maybe it's 3, maybe it's 4. I don't really care. If you look at the degrees of freedom of an actual cubic spline, well, you see that very similar. I mean, slightly higher, especially at the higher number for k. And that effectively translates into these weird confidence intervals at the edges, right? So even though it seems like a very small increase in MSE, lower is really truly better there. Good. Now, if you compare a spline, be it a cubic spline, but preferably, of course, right now, from what we know, a natural cubic spline, it is really superior to polynomial. So if we now take some data, well, same data we've been looking at all the time, and we fit a polynomial of degree 15, because why not? And at the same time, we fit a natural cubic spline also of degree 15, namely 15 cut points, right? So 16 distinct areas. And if we now look at how it fits the data, we have this picture. What you see is that the polynomial, which is the blue line, so across the data here, it actually does a reasonable job. But at these edges, when there is little data, it does weird stuff, right? I mean, shooting off like this. So if we would use this model to predict the wage of somebody of, let's say, the age of 5, it would say probably that these people make billions of monies. That's nonsense. If we ask it to predict the wage of somebody above 80, as you can see, it dives deep. Probably these people have to bring money. Doesn't make much sense. Whereas the natural cubic spline, at the edges, it does something that is very sensible. And within the data, well, there are a few bumps, which you might say, okay, well, that is odd. Yeah, maybe we should not have chosen 15 here, right? This is just for the sake of the example. But effectively, for this group, there's a little bit fewer people, you can see this here, that have higher wage, right? So at this age of 42, which is coincidentally my age, and there is a bit more people who make slightly less. Okay, so that could be. And the natural cubic spline fits this, and the polynomial in this case does not. This is just a data-driven effect, nothing to be worried about. What is important, though, is that at the edges, we reduce the wiggliness. That is important. Good. Okay. Now, if we've now gone from cubic splines to natural cubic splines, and we fixed this edge behavior, you might say, okay, I don't even want to choose k, right? I mean, I'm meh. Or you might be otherwise interested in saying, okay, well, if increasing k essentially doesn't harm, why don't we crank it up all the way to the max, right? I mean, that's why don't we just crank it up to n? Well, we have n data points, n cut points. Okay, well, let's do n minus 1 because otherwise we have empty bins, right? But, yeah, good idea. Good idea. This is called a smoothing spline. In a smoothing spline, we because we now really have one bin per data point, it all of a sudden becomes non-parametric. Okay, why? Because we're still fitting a polynomial. But yes, but no, we only have one data point. There is no polynomial to be fitted truly. The only thing that we have is that we want within this bin that particular data point to be predicted, and we want to make sure that at the edges, at the knots, the function that we're fitting remains d minus 1 times continuous, and the derivative needs to be the same. Okay, my brain was a brain fart. Good. So what we're doing, we're now going to be evaluating the wiggliness of the function by taking the second derivative of the function we're fitting. And, well, see, if you just have to value the function, that's so interesting. First derivative is the slope. Second derivative is the wiggliness. The more wiggly the function is, the more prone to overfitting we are, right? So what we effectively do when fitting a smoothing spline is that we introduce a penalty on how wiggly the function is, on how large this second derivative of the function is. And then effectively, we arrive at this. So we want to predict the target value, y at I. We're fitting a function g over xi. We take the mean squared error. And then, hey, this thing looks very similar to what you already know from ridge regression. Namely, we have some penalty, lambda to weigh the penalty. And what is the penalty? In this case, we just integrate over the wiggliness. So it's similar, not exactly the same, but similar. Now, what do we get? We now have a way of choosing directly the degree of freedom, and don't have to bother like how many knots and where to place them, right? All those problems have been thrown out of the window. And what we get is that, well, here if you have two functions, right? One with 16 degrees of freedom, pretty much the same as we saw on the previous slide, and one with 6.8. And as you can see, that the smoothing spline, look at how smooth this blue line is, right? Compared to the red one, which is indeed a bit too wiggly. You have the same weird bumps that we saw with the natural splines with a degree of 15. Good luck choosing a degree of freedom of 6.8 for a natural spline, right? I mean, maybe 7 will do equally well, but here we can really tune it pretty much to the max. Now, it can be shown that if we want to minimize this function, right, for a given value of lambda, obviously, it actually is a natural cubic spline with a knot at all data points. So effectively, smoothing splines and natural cubic splines are essentially, well, joined at the hip. They're essentially the same. They are just different formulations that allow us to, in this particular case, to directly focus on the smoothness without having to choose the location of the knots, because the knots are everywhere. And it's just a special case. And it's a very pleasant special case. Another way of looking at it, just like with ridge regression, is that we're, because of this value lambda, we're shrinking the degrees of freedom. And essentially, smoothing spline is a shrunken version of natural cubic splines with k equals n knots. What does this mean in practice? I mean, before I start to explain how to choose lambda in a meaningful manner, smoothing splines are really, this is your weapon of choice. Before I started lecturing EML, which is now I've been doing for, this is the 6th year, I didn't know of smoothing splines. It was never taught to me. I never encountered it. It is by now really my most favorite machine learning method. Whenever I have encountered a regression problem, smoothing splines. Really, I mean that for causal inference, we needed some regression, smoothing splines. I mean that if you want to predict something, smoothing splines. Always smoothing splines. They're miraculous. Some people these days may say, okay, but why not a deep neural network? Yeah, okay. Well, then I need to tune so many parameters, need to make so many choices. Smoothing splines. Perfect solution almost always. But, except, of course, if we don't choose lambda right. So how do we choose lambda right? Lambda is the amount of shrinkage to the spline, right? We're effectively reducing the degrees of freedom, how wiggly it can be. So, now, how can we determine the wiggliness? Let g now be, g is the function. We're going to estimate g for a particular value of lambda. what do we now arrive at? Well, we have the output value that we want, that is y, and we have our spline, right? And the spline is then, again, according to lambda. So effectively, our function is now reduced, our function g is effectively reduced to just vector of the fitted outputs, right? I mean, that's essentially what our spline says, right? And that for a particular choice of lambda. Yeah, if we now look at it in this linear algebra approach, then just by looking at the trace, so sum of the diagonal of this matrix S, which is the definition of our spline, that essentially gives the importance of how wiggly does one point really want to be, right? I mean, so does it need to be in the optimal assignment if we want to predict these values of y as well as possible, minimizing the MSE like this. The trace of S gives us the effective degrees of freedom. So this means that for a given value of lambda, you simply fit your function, right? There you are, good, right? You know how to do this. This is relatively straightforward. Effectively, you can just run function, I mean, that is implemented in Python, in R, or whatnot. You get your output values. You can determine then this matrix S, and just by running a trace on it, there you are, right? That's the effective degrees of freedom. There's also standard implementations for this, and in the assignment, I think we're going to be playing with the degrees of freedom a bit further. Now, given that we can now determine the degrees of freedom, we can also now use this to choose it by cross-validation. For example, by leave one out cross-validation. Leave one out cross-validation is in many ways my least favorite way of doing cross-validation, because way too much repetition and way too much, well, that has been discussed in the previous lecture. But the nice thing about leave one out cross-validation is that it allows many things to be written neatly in analytical form. So we can write down the residual sum of squares for cross-validation, certain value of k, with regard to lambda as simply the sum over all data points, where we have the output, we have our fitted function, estimated function g, lambda, and we take, we leave the 1 point out, right? That's the 1 point that we don't want. We look at the square of errors, and this we can now rewrite in terms of this matrix S. That allows us to directly choose essentially the value of lambda. Good. Time to move on already. So normally, if this would be a real lecture, I would say, let's go for a break. I'll allow you to take a break, to press pause, but otherwise, let's just power on. We're going to be powering on towards local regression. A bit sad because I love splines, but I mean, there's not so much more to be said here without really diving into the deep end of theory. We don't want to do this here. We are more users or perhaps even abusers of splines. Now, let's go to local regression. Local regression is a very neat extension of k nearest neighbors. Recall that for k nearest neighbor regression, we want to know what is the output for, let's say, this is x1 and this is y. Then for a particular value, let's say 0.05, we would like to know what is the value of y, right? So what we normally would do in k nearest neighbors, we simply pick up those k points closest in the x direction to our query point. And then we spit out the average, or perhaps a weighted average. We can do something, right? And that is generally what k nearest neighbor regression is. Similarly, for classification, you would pick up the k nearest points, and then by a majority vote, that is the label that you spit out. There is essentially no magic. You've seen the pictures in earlier lectures where it sort of creates this staircase type of you call it a landscape across the input values towards y. Yeah, there's a little action there, and it's every step is precise and is meanwhile just flat. Can we do better? The answer is yes. Namely, if we do take the k nearest points in terms of x, which are now these the orange points, if I'm not mistaken, should be. And what we now do is, rather than just take an average over them, which is, that would just be a flat line, right? An average of the value of y, I mean, we can now fit a function over these points. Well, an average is a function. I hear you saying, yes, yeah, you're right. An average is a function. let's be a little bit smarter. Let's fit a linear function. Okay, cool. I hear you say, yeah, we can do that. I mean, that is not a problem. It's a little bit of data and we know how to do linear regression, not a problem. But then the key idea in local regression is that, well, the nearest of the nearest neighbors, they should somehow intuitively have more importance than, well, the furthest of the nearest neighbors. By which I mean to say that if we want to query for 0.05, then these points in this area, we should somehow weigh more than these points over here. We should not ignore them, because that would mean that we're effectively doing k nearest neighbors with a value smaller than k. But we don't want to have our line too much influenced, or our line or whatever function we fit, too much influenced by them. Rather, the line should listen to this. So what do? We take the k nearest neighbors. We apply a weighting function, which is called a kernel. We go at that in a second, which is now depicted by this, well, greenish. I mean, it's more like a sick greenish color, but okay. This is essentially what we're drawing, in this case, a Gaussian around it. And the Gaussian determines that, hey, the higher the weight at that particular value, and it's the highest, of course, at the query point, those values of those nearest neighbors, we're going to weigh very strongly and in towards the tails of the kernel function of the Gaussian. Well, we barely pay attention to them. And what we can now do is we now fit a linear function accordingly, and we get this particular slope in this case, so this dark orange slope. And as you can see that if we now look at what is the true curve, it's the blue one, or if we were to fit a curve using, well, whatever, let's say a spline, right? We actually get a pretty decent estimate just by looking locally. Okay, neat. Let's see if this also works somewhere else in the data. Here, in the middle of the data, this also, I mean, the slope actually fits remarkably well. This is pretty neat because we're now always fitting a function with a remarkably low degree of freedom. I mean, this is a linear function, right? I mean, and barely make it less free. I mean, that would just be a constant. And then we're back to standard k nearest neighbor regression. So effectively, we now have a method that is on the one hand very flexible because, well, it adapts really to the local part of the data. It is non-parametric in that sense, right? I mean, that's, even though the function we're fitting is parametric, but for any query point, we will fit its dedicated model. But it means that if the data size goes to infinity, there are infinitely many possible models. That some of them might have the same slope, doesn't matter, infinitely many. So with local regression, we have a non-parametric approach to fit a simple function, and a simple function is good because then we can fit the parameters very well. And in practice, this also leads to very good predictions. This is what you see here. So now let's make it a little bit more formal. The weights of the neighbors, like I already explained with the picture, are calculated through a weighing function or a kernel function. Kernel functions we're going to see a number of times later in the course, amongst others in kernel machines, support vector machines. And kernels, I mean, always sound a bit like magical. A kernel is simply a function applied to part of your data. It's really, that's all it is. I mean, you apply a function to part of your data, you get a different value, you work with that value. Done. So, in this particular case, the kernel function is going to be a Gaussian. So that is effectively what you use. So this is the blue one, right? So, and the kernel function, this Gaussian, then gives a certain importance to values. I mean, so the further away, the lower the importance. And that's what we'll be working with, right? So there's really no magic when people start using kernels. It just sounds always a bit scary. You can use different kernel functions. In general, you like the symmetric behavior of a Gaussian, and you like the fact that the main mass is at zero mean, and then it tapers off. But sometimes you want to, well, give it a slightly different shape for. Because in a Gaussian, essentially, no matter how far away we go, every data point gets some non-zero probability mass. And yeah, that's a bit stupid if we want to fit now a function on for one particular prediction. But effectively, because there's a non-zero probability even for the furthest possible data point in the data set, we also need to take that data point into account and fitting the focal function. I mean, ain't nobody got time for that. So we can use the idea of a truncated Gaussian. We really say, okay, you know what? from 3, -3, or respectively 3 onward, we just truncate it to 0. Okay, but if we're doing that, then we can also change the shape of the function. For example, I always have trouble pronouncing this, the Epagenikov function is essentially 0, except when it's not. And then it takes a parabolic shape. A tricube function, which is simply particular value, the difference from the mean cubed, and that difference we cube again, such that we always have a positive value. There we are, up. And the shape is now chosen by t, of course. And that gets also like a Gaussian shape, which naturally is 0 here, but it's a bit more smooth at the edges, right? So the Epagenikov has a very non-continuous shape here, which is a bit meh. Effectively, if you prefer a Gaussian, use a Gaussian. If you prefer a t-distribution, use a t-distribution. If you prefer one of these two, go ahead. The key idea that is important to remember, to work with a little bit, only use the local points, and the more local they are, rely on them more strongly. Okay, so in kernel land, there's a few other important notions to keep in mind. So each of these functions, they essentially distribute the probability mass, right? So how much are we going to listen to local points slightly differently? But the key idea is that the ones closest to the query point are the most important, right? They get the largest weight. Now, the width of how far we spread this probability mass, this is called the span. So the width of the kernel is also called the span. And that is effectively the key ingredient for any kernel function, because any kernel function you want to apply on the data around a data point. So it has to be 0 mean, so that degree of freedom is gone. So the only true degree of freedom it has, besides the choice of which function to use, but that is totally yours, is this width, the span of the kernel. So how much of the data does it span? How much of the data do we truly need to take into account? Formally, you could say that a distribution can have compact support. Compact support means that it only looks at part of the data and it doesn't assign probability mass to all the data points like Gaussian does. So if it does not have compact support, hello Gaussian, or non-truncated Gaussian, you need all training data for every prediction, even the furthest away points. So hence people in practice use either of the two functions I showed or a truncated Gaussian, which is then not really a probability distribution, but okay, max, we don't care. So, now, how do we fit locally? Well, that's simply a linear function where we weigh, depending on how far away a point is, the effect of the prediction being wrong. So we don't, we don't care that here the prediction is a bit wrong, because what we're mostly interested here, we're just using these points as sort of not high leverage points, which you remember from linear regression at the very beginning of the course, but sort of like low leverage points to get the slope approximately right. Because if the data here, if these data points would not exist, only here at the top we have data points, it would be better to have the slope slightly more tilted. Whereas it's the opposite, right? If these data points would not exist, but they would all here, then we should adjust the slope ever so slightly here. Even though these data points are not that close to the query point, and hence the effect should not be that large, hence low leverage, but they should have some effect. Good. So let's now look a bit more closely at the kernel. We have function k for kernel. We have a smoothing parameter, lambda. Still remember this one. We have a test point x0, and then we have some data point x. Effectively, what we're looking at, what the kernel tries to measure, is the distance, distance d of the query point to the data point in absolute terms, right? So the further away this the point is, actually the less influence we want. We have then the span. This is essentially around the test point, right? Because it's not determined on the data point, but really on the test point. It's 0 centered, right? So the span as smoothing is already basically woven into that, right? So this is, let's say, the parameter of the Gaussian. Let's call it that. So where we place this Gaussian depends on the test point. This is x0, and then how much we smooth things out, that is lambda. Now, if we crank up lambda very high, what do we have? we will have very low variance because we include essentially all of the data. All of the data is going to be important. We're going to have very high bias because effectively just fitting linear function over all the data. Now every function is always the same, right? That's one analysis. Another thing to think about is that we could, in theory, use different spans for different data points. I mean, why not, right? I mean, nobody's going to stop us. But if we don't, if we actually choose the same everywhere, and in fact we remove the entire the entire function, we always set it to some value lambda, then all of a sudden the kernel starts to become metric. Why is this important? Essentially, the space over which we're measuring, and what we're measuring is how important is the distance from the query point to any other data point. If this is metric, then we can start to compare distances, and we have all sorts of analytical goodness. In addition, what we're also going to get is that biases are going to be constant over the data range. So we're not more biased in this part of the data than that part of the data. So this is a desirable feature. The variance is going to be inversely proportional to the local density, which makes sense. The more data points we have, well, the lower the variance. The lower the number of points, the lower the density, the higher the variance, which is exactly what you would want, right? So we want to have metric kernels, and hence just choose this thing constant. No worry there. Another thing to think about is that, well, we're applying this kernel function over a certain set of neighbors, right? We're looking at a window width. So the nearest neighbor window width, also consider this S of k, also has a certain span, right? Which is essentially, I mean, the distance of query point to the kth neighbor has, interesting enough, the opposite behavior. So the variance is going to be constant over the range because, well, we essentially look over the entire window. But the bias is going to be inversely proportional to local density because there where we have lots of data, we have a very small window, and there we are. So how does this now work? If you want to put this in practice. So this is the moment where you should start paying attention again, right? If you didn't want to learn more about kernels, then would skip, but right now you need to pay attention. Local linear regression, we of course can always also use polynomial or even splines if you wish. I don't know why you would want this, but okay. Let's stick with local linear regression. We are interested in predicting the value at some query point x0, right? So we take our kernel function. Let's take the Gaussian because it's, or the truncated Gaussian because the easiest to think about. We assign effectively a weight, k, for every data point I with respect to the distance to training point 0, the query point, to every training point. Some of those we're going to get a value of 0. If they get a value of 0, the kernel says, okay, I don't like you. There you are, right? I mean, that's, we can just throw them out. We don't have to learn over them. Already said earlier, we're now going to fit a model over the data points according to this weight, and we're going to weigh them. So we care about the local points, the errors to make local points more than the points that are further away. How do we do this formally? We fit just standard least squares. You know, you love it. We find beta naught, okay, fine, and beta 1, and so on and so forth, such that we minimize the sum of squared almost errors, meaning got you there, kernelized errors. It is not the pure distance between yi, the target value, intercept, and whatever we fit. No, we kernelize it. The further away the point I is from the query point, the smaller the weight that the kernel will give to it. And if we then, well, look at the squared value of what we now get from that, we really don't care. We really don't care. So essentially, there's no magic. We just weigh, right? We look at how far is the prediction. This is how we weigh it. If the data point is not even in the k nearest neighbors, this value is going to be 0, so we can completely ignore it, and there we are. And this is then what the function that you get. Oh, good. So local linear regression, depending on the span that you choose inside the kernel, will be more or less wiggly. So we have examples here. For a very small span, 0.2, you see that it's way more wiggly, which may be counterintuitive until you realize, hey, small span, I'm only looking at very local points. So yeah, small differences locally are going to make a large impact. Whereas if we choose a larger span, we look at more points, we're averaging out, the degrees of freedom are going to drop, the effective degrees of freedom, and you also get a smoother line. So, how do we choose the span? Cross-validation. The degrees of freedom, how do we determine them? We can again do this using the same technique we saw earlier for splines with leave and out cross-validation. There is essentially no magic there either. This was an example for really simple local linear regression where we only have one variable x that we want as input. Trivially generalizes to multivariate, so to multiple x's at higher dimensions. No problem. Now, what is of course going to be a bit tricky if you push it. So whether it's 3 or 4, that depends a bit. Actually, I think around 3 and 4, you need to start regularizing probably, because if you have now really high dimensional data, let's push p to 100, something like this. Then, and we just look at a few data points around, it might well be that for the one data point, the query point x0, the line is going to be like this, and for the next one, it's going to be shooting off in this direction, and that one in this direction. And so you get essentially some smoothness issues for higher dimensional data that you don't want, and that is where an extension of multivariate, or an extension of splines is going to save the day, because effectively local linear regression is kind of doing splines without bins and just locally, right? You can conceptually connect the dots. Good. That was it for local linear regression. Final topic of today, coming up right now. Generalized additive models, GAMs. GAMs, I have to again admit, before I started teaching EML, well, actually, I had heard of it. I mean, I have to be honest, I had heard of it in my introductory courses in machine learning from data, that was called. There was some small subtopic on GAMs. I mean, and I forgot about them because, yeah, who needs those? Then I started teaching EML, and actually GAMs are fantastic. GAMs are fantastic, and that both conceptually and in practice quite often too, but particularly conceptually. You can reduce many existing models and many advanced concepts to GAMs. For example, if right now many of you might be interested in, let's say, explainable machine learning, in the sense that we can train some super fancy deep neural network. You don't know yet how, but you have something that predicts super well, but nobody has any idea how to do it. And then you have advanced explainability techniques like Lime or Shapley values or whatnot. I'm just throwing a few words at you that you might not know, but all fine. Effectively, what those techniques do, and those are really like hot of the needle and new, they essentially cast this super fancy deep neural network into a GAM. And well, once you've done that, then you can use lots of analysis techniques that you already know, and you can analyze this GAM in a way that gives you something to say about the underlying model. So that is one of the reasons why GAMs are actually super interesting. They're also interesting in other ways. So let's focus on those right now, right? But I'm just pointing out that the things that we're teaching you in EML, sometimes they might seem basic or super complex, but trust me, these are really the elements of machine learning, the building blocks. But each of these techniques that we're teaching, you still see them in day-to-day practice in machine learning right now, but, be it in research, be it in industry. Good. So that's it, GAMs. Effectively what we're doing, let me try to put the example. Yeah, you know linear regression, multiple linear regression, right? Looks like this. We want to predict some value y, and then we have, well, some, this is query point xi. I mean, let's forget about that for now. We have x1, x2, x whatever, right? We have, and each of those only get one beta, right? So it's basically linear in beta. This is what I said at the beginning. And perhaps you wonder, okay, why is this so important? Why is he hammering so much on that? This is just one big addition of super simple linear functions. So it's a linear addition of linear functions. Now, by making the basis functions, nonlinear. So having quadratic or cubic functions. So let's say this is x1, this is x1 squared, this is x1 cubed or whatever, right? Beat. Beat sounds bad. Okay, kth. Then we do have all of a sudden the possibility to fit a nonlinear function, but it's still one long addition of linear functions. It's namely just some coefficient times x to the power so and so much. This might have already dawned on you. What if we now replace this beta 1 times x1 and beta 2 times x squared with a function? Why don't we rewrite it like this? Because effectively that's what we have, right? It's now we have one long addition, as long as here, but now of functions of x1, x2, and so on and so forth. Effectively, what we're hiding here is that this function 1 is simply a beta 1 times x1. This is the direct translation of that function. But the moment we start to write it as a function rather than just as a beta, that allows us a lot more flexibility, doesn't it? Because this function, it can be just a beta, but it can also be something else. It could be a spline, right? You already know what a spline is. I mean, that's so we could have a spline for x1. Let's call this f1. We can have a separate spline for x2, and so on and so forth. And there is no beta anymore. We now have a whole collection of splines. The only beta we still will have, or we should have, otherwise, I mean, things get ugly, is beta naught. Oh, this is just the intercept, right? I mean, to just average, to make sure that's on that there's a reasonable average. Okay, so that simple concept. Read this as a simple linear function, give it the name f, and then, well, once it's f, it doesn't have to be a simple linear function, but it can be any function. That is a GAN. That is what makes it a generalized additive model. Additive because we have a bunch of functions, but generalized because we're now speaking about functions. So let's go to an example. For the wage versus wage thing, we have some beta naught, that would be the average wage after all the regression is done. We have some function over year, some function over age, and some function over education, and then some noise. And each of those functions, well, we can fit different things. How are we going to do this? Primarily splines. We don't have to, but this is very nice. For year and age, this works easy because they're both continuous, right? And we're going to use natural splines because why not? You could use a smoothing spline. Had I written the book, I would have used a smoothing spline. I love smoothing splines. Now, education is not continuous, so darn, right? I mean, what can we do? Well, we'll just create some dummy dummy variables. High school, I think it is below high school, above high school, but below college. I don't know exactly. This is college, and this is above college level. And then, well, we can fit constants for each of these dummy variables. Okay, what we now get, if we look at those functions after fitting, and yes, I haven't explained how to fit it yet, but we'll get there in a second. It would look something like this. We can now have in order to predict the wage, right? I mean, the function over year, it does not have to be linear anymore, even though it looks quite linearish, right? We allow it 4 degrees of freedom, but as you can see, for year, linear is kind of fine, right? But, of course, nonlinear allows to basically say, okay, well, look, in 2007, 2008, the average wages did not rise as much. This is the start of, well, a previous economic crisis. I mean, this is around the time that I graduated, so job market was not that great. I remember that very well. So wages did not grow as much, and then they started growing again. And that is a behavior that you can fit with a nonlinear function, but not the linear one, right? So already generalized additive models add something to the game. Now, in terms of age and wage, I mean, are they linearly related? We already saw, not quite, right? We really need to sort of bend over backward to get this done. And that's what you see is that actually between the age of 20 up till 40-ish, there is an almost linear increase, right? And that then afterwards, such a taper off. I mean, people drop out of the workforce, maybe because they have kids, maybe because I don't know, but they retire early. And then after a certain age, somewhere in the 60s, people really start to retire and the wages drop again. Again, something that with a simple linear function you can't fit. And by just adding a number of basis functions, so h squared, h cubed, perhaps you can capture it somewhat, but what is the linear function to the cubed value of h that really matches reality? I don't know. How would you interpret this? This is actually much nicer. You can directly see for h what is the effect. Low age, you have, compared to the average wage of the entire population, you have a negative effect. And at let's say the peak age, there it bumps it up. Same thing for education, except here we start to see something a little bit weird. We have, for each of these education levels, right? Remember, lower than high school, and so on and so forth. What are now essentially the added bonuses, right? What is the level from which we have to see? You see that there's particularly high variance, especially here, because, well, there's very few people in the data set that have not even a high school diploma and essentially make any money. So as we'll see in a later slide, if we not throw these people away, right? I mean, we love these people, but I mean, we throw them from the data set and then refit stuff, then actually we get better predictions across the board. This is when we use, so this is for a natural spline. If we use a smoothing spline, I'm just going to flip-flop between these two slides, and I hope the recording picks this up and it's not too fuzzy. You see that there is not so much difference, right? But the only difference that you see, and this is perhaps then the argument against smoothing splines, that here at the very edge, the confidence intervals are slightly wider than they are for natural splines. But yeah, that is natural, because natural splines only have these linear functions at the very edges. Smoothing splines, of course, there we don't have to choose the number of cut points. We can directly tune the degrees of freedom. Okay, good. How do we fit a GAN? Because you know how to fit a linear regression model. That is by now hopefully quite straightforward. But if we now are not just fiddling with beta 1, beta 2, beta 3, but actually we're fiddling with an entire function, and in every learning iteration we can consider a completely different function f1 and at the same time a completely different function f2, and so on and so forth. And wow, that is a lot of freedom. And obviously, if I choose function 1 very differently, then probably I have to choose function 2 very differently, because they kind of should be tuned to each other. So how do I learn this? I mean, is this even possible? This is something where people broke their head over for a while, but we came up with a solution. And it's simple, because people like simple solutions. It's called backfitting. And backfitting effectively comes down to, we fit every function at a time, and then we start over and we refit the first function, and then we refit the second function, and then we refit the third function, and then we loopity until we're happy, we're done. So what do we start with? We first choose beta naught. Beta naught we can determine analytically. So this is just like, well, the average over the output values. Done. This means that every function that we're going to fit is now going to be essentially a function that increases or decreases from this overall average, right? So this beta naught is really a data-driven thing. It's not really something that says something about the world. Okay, now we're going to cycle. This is what I said. We start the function. We're going to first, for j is 1, we're going to estimate function 1 by applying, for example, in this case, so this is where we cubic smoothing spline, what we're fitting. You can choose whatever you want, but smoothing splines are nice. So we fit the smoothing spline, but what we do, it's of the jth input only. So we ignore all the others, right? I mean, that's all other features. So if we're looking at j as 1, right? x2, x3, x4, we completely ignore them, right? So we keep those functions constant, and we only see like, okay, we're going to change function 1. Then next up, we determine what is now the average of function j over all points. We subtract it, and there we are. This sort of balances things out. Why is this balancing necessary? Because we want each of these functions really to adjust based on this overall average, right? So if a function starts to become non-zero mean, then the other functions need to compensate for the non-zero meanness of function. Let's say function 2 needs to now adapt for the non-zero meanness of function 1, which kind of screws up the interpretation of function 2. And if function 2 doesn't do its job well, then function 3 has an even harder time, and then errors can accumulate. This problem exists mostly just in theory. In practice, if you use a proper function learner, for example, smoothing splines, then actually this is not necessary. But yeah, it's because of imprecision, machine precision, because of maybe a bug in your code or whatnot. Let's keep this in. Let's keep this in. We do this for function 1, keeping all the other functions constant. Then for function 2, keeping all the other functions constant, and so on and so forth, until convergence. So, depending on how you're smooth and whatnot, this essentially comes down to the Gauss-Seidel algorithm for fitting a system of linear equations, where you also fiddle with one, keeping the rest constant, fiddle with the second, keeping the rest constant, and so on and so forth. So in that sense, GAMs were not like a complete miraculous new invention. Just turns out to be a smart adaptation of what we already knew to a new application. Now let's go over the advantages or disadvantages of GAMs. GAMs are non-parametric because, well, you can fit a function for every predictor, and each of these functions can again be non-parametric, so the entire thing is non-parametric. So, and especially if you use splines, super effective and easy to apply, there you are. So you don't have to basically see if you now want a linear or a cubic or this function or that, so you can basically throw stuff at it. If you have enough data, then the non-parametricity helps you because you'll get more accurate predictions. If you do not have enough data, you're not in for a good time. If you have little data, GAMs are going to be right. I mean, it's not on this slide, but I mean, trust me there. Now, one other nice thing about GAMs is that the model is additive, right? F1 of x1, F1 of x plus F2 of x, and so on and so forth. That means that we can directly see what is the influence of a variable if all the others are fixed, right? This is what these plots that I showed you. You can really see, like, oh, wait a second, this is what is going on. Now, that is at the same time also a downside, because recall from earlier lectures, sometimes you want to fit interactions between features, between x1 and x2. Can a GAM do that? Well, only if you really consider the basis function x1 times x2, or you fit explicitly a function over x1 and x2, right? So that can figure out itself if there's an interaction, which means that if you sort of think out of the box, the ultimate GAM would actually be beta naught plus a function over x1, x2, x3, and so on. Yeah, but that, if we then back into the box, then we realize, wait a second, that would be the function that we will try to fit in general. That would, no. It's not going to work unless you apply end-to-end learning. This is where deep learning shines, but that is not an element of machine learning yet. So we'll keep that for this. Yeah, the smoothness of the individual functions, we can again summarize by the degrees of freedom. It's just a spline. There you are. Well, I think everything in this slide is now covered. You might ask, I doubt anybody asks themselves that, but maybe some of you ask, can you use a GAM then also for classification? Well, if you ask this, then it's basically answering the question, because all the things we've been discussing you can use for the one or for the other. So if you want to use a GAM for classification, just plug it into logistic regression and bam, there you are. But all of a sudden, the model changes from the standard and familiar linear form, right, with all these linear functions, to look at this, we have, again, a linear additive form, but the linearity here disappears now with a set of functions. The way it's being fitted works exactly the same way as what we just saw. Right. So no surprises there. Yeah, now let's go now for a classification example. We fit the GAM like here. Here we have the example. So in year we get a function that is essentially linear, right? I mean, that is great. For age, we really want to have a spline that can sort of pick up that young people don't make so much yet and that old people don't make much anymore. There we are. And now for the education variable, this is what the commenter already said earlier. The confidence interval for people with less than high school, was already quite wide in just the regression task. But if now the task is to predict who makes more than 250K per year, those people that don't have a high school degree, not so many of them make that much. So you get a giganormous confidence interval here, and it kind of hides the action over here. So if we remove those people from the data, then actually, and we refit everything, then you can see that, hey, you should pay attention in school. So I hope that you paid attention in this lecture, because, well, look, it's good for your final wage. And this brings us already to the end of this lecture. Yeah, and actually I'm very good on time too, so I'm happy. I hope you're also happy. The only thing that makes me less happy is that this lecture was not in person, but that we're going to change. On the 4th of January, the second lecture that I'll be teaching, the 9th lecture of Elements of Machine Learning, will be in person in the Günterholz, and I'm looking forward to seeing you there. And until then, I wish you, well, very good end of the year, Merry Christmas, Happy Holidays, Gute Rutsch, and all that. See you on the other side. See you in 2024.